Plotting the optimum altitude over time gives us the graph shown on screen. In order for the aeroplane to maximize the specific range, the aeroplane must stay with the optimum altitude as the optimum altitude slowly increases. Climbing in this way is sometimes called a cruise climb. But carrying out a cruise climb is not always possible, since air traffic control restrictions and airspace congestion may predetermine flight cruising levels. If this is the case, in order to stay close to the optimum altitude, step climbs may be performed. Step climbs essentially mean that the aeroplane climbs to about 2,000 feet above the optimum altitude and levels off. As fuel is used and weight falls, the optimum altitude will increase to a point where it is again 2,000 feet above the aeroplane's current level, but it can take up to 3 hours for it to do so. At its current level, the aeroplane can then climb 4,000 feet and level off, so that it will once again be 2,000 feet above the optimum altitude. But, if the last step climb is within 200 nautical miles of the top of descent, then the fuel saving is negated and the aeroplane should remain level. The step climb process can be repeated throughout the cruise, and it helps to explain why the cruise altitudes at the end of the flight are higher than at the start. Carrying out step climbs in this way, rather than always staying with the optimum altitude, will increase fuel consumption by about 1% and therefore decrease the maximum range by 1%. This may not sound like much, but over a year, a typical 747 would have used an extra 34,000 tons of fuel. If an aeroplane did not even step climb and simply remained at a constant altitude during the cruise, then the aeroplane would increase its fuel consumption by 10% compared to flying constantly at the optimum altitude. This demonstrates just how important altitude and speed control are in the cruise for a typical commercial flight. Having discussed the effect of altitude on the jet aeroplane, let us now consider the effect of altitude on the propeller aeroplane. In general, though, we may say that most turbopropeller aeroplanes operate significantly lower than their jet counterparts. Turbopropeller aeroplanes seldom operate above 30,000 feet, and therefore never really suffer from the effects of getting close to the speed of sound. Turbopropellers are based on the same engine design as a pure jet. Therefore, the effect of altitude on the turbopropeller is very similar to the jet aeroplane. As altitude increases, the increasing TAS and slightly decreasing specific fuel consumption help to improve the specific range. However, this benefit is offset a little by the increasing power required at higher altitude. So, while specific range does improve with altitude, above 10,000 feet it only improves by a small amount. The choice of altitude may depend more on the wind considerations and the time and fuel considerations involved in climbing to the selected altitude. The other type of propeller aeroplane is that driven by a piston engine. You will recall that the piston engine aeroplane has a more or less fixed specific fuel consumption, even though specific fuel consumption is lowest at high manifold pressures, low RPM, and with the mixture correctly set. Therefore, the only remaining variables in the specific air range formula for the piston engine aeroplane are the true airspeed and the power required. As the aeroplane operates at higher and higher altitudes, the power required to maintain the range speed will increase. This, of course, is detrimental to range. However, as altitude increases, true airspeed increases for any given indicated airspeed. This fact offsets the increase of power required, and therefore the specific range slowly increases with altitude. However, the aeroplane will reach an altitude where the throttle needs to be fully advanced to keep the selected speed. This altitude is called the full throttle height. Beyond this altitude, the selected power and selected airspeed cannot be maintained, and the aeroplane will slow down. Very soon after this altitude, the true airspeed will also start to fall despite the decreasing density. This fact, combined with the constantly increasing amount of power required, means that the specific range will decrease. As a result, maximum specific range will be attained just after full throttle height. The effect of headwinds and tailwinds on the range of the aeroplane can play a significant role in the choice of cruising altitude. For example, if there is a considerable headwind at the selected cruising altitude, this will be detrimental to the range. In this case, it may be beneficial to operate at a different altitude where the winds might be more favourable. In large commercial operations, most of these considerations are dealt with prior to the flight by the flight planning personnel. However, in smaller operations, and if conditions change in flight, a pilot may have to carry out a wind-altitude trade-off calculation. Information enabling the pilot to do this is usually given in the aeroplane flight manual, an example of which is shown on screen. The graph shown on screen shows the relationship between the speed of the aeroplane and its range. Shown here is the speed for best range, which for a jet aeroplane is 1.32 VMD. In commercial operations, this speed is more commonly referred to as the maximum range cruise, or MRC. However, maximum range cruise speed is seldom flown. Usually, a higher speed is used. Looking at the top of the graph, you will notice the line is fairly flat. This means that a significant speed increase can be achieved with only a small compromise in range. This higher speed is called the long-range cruise. The long-range cruise speed is about 4% higher than the maximum range cruise speed, and as such, the specific range reduces by about 1%. The reason for using this higher speed is simply that there are costs other than fuel which need to be considered in commercial operations. A more detailed explanation of the relationships of these costs and how they affect the operations will be dealt with later on. This last section on the general performance principles in the cruise deals with summarizing the performance speeds using the drag and power required curves. Firstly, we will go through the performance speeds on the drag curve. You may recall that there were three reference speeds. These were VMP, VMD, and 1.32 VMD. Since this is the drag curve, the speed on the bottom of the curve is called VMD. The other two speeds are VMP and 1.32 VMD. VMP is about 0.76 lower than VMD. 1.32 VMD is higher than VMD and is found on the tangent of the drag curve. These three reference speeds mean different things for different aeroplanes, and knowing which reference speed is to be used for a specific performance task is important. For example, you may recall that the best endurance speed for a jet aeroplane is VMD, but the best range speed is 1.32 VMD. Best endurance speed for a propeller is VMP, but the best range speed is VMD. There are other speeds though. During the climb lesson we learnt that the best angle of climb speed, Vx, is for a jet aeroplane VMD, but for a propeller aeroplane it is VMP. The best rate of climb speed, Vy, is for a jet 1.32 VMD, but for a propeller aeroplane it is VMD. Lastly, during the descent lesson you learnt that the speed for the minimum angle of descent, or best glide speed, is VMD, and the speed for the minimum rate of descent is VMP. It's obvious that so many speeds may cause confusion to students. Placing the speeds together in this way helps you to see where they are in relation to the three reference speeds and in relation to one another. What is equally important though is for you to have a tool which you can manipulate to give the desired results. This is what the graph aims to provide. You may remember that as weight increases, the drag curve moves up and to the right. This means that not only drag is increased, but also all the performance speeds are higher. The reverse is true as weight is decreased. The drag curve moves down and left, showing that drag decreases and the performance speeds are lower. As gear and flap are deployed, the drag curve moves up and left, showing drag increases, but the performance speeds are lower. Retracting the undercarriage produces the opposite effect. Drag decreases, but the performance speeds are higher. Using the graph in this way, we can simplify a lot of the material that you need to learn. Just as in the previous section where the performance speeds were shown on the drag curve, we can do the same with the power required curve. Firstly, the three reference speeds need to be identified on the graph. Since this is a power required curve, the speed at the bottom of the curve is the velocity of minimum power, VMP, as shown. The next speed is VMD. This is slightly higher than the VMP and is found at the tangent point on the power required curve. The last speed is 1.32 VMD and is shown here. It is now possible to place the performance speeds we described in the previous section beneath the relevant reference speeds. Doing this completes the placement of all the speeds on the power curve for both jet and propeller aeroplanes. As before, the power curve can be manipulated to show the effect of certain conditions, giving you a tool to solve basic problems. Increasing weight will move the curve up and right, therefore showing the increase in power required, but it also shows that the performance speeds are higher. If weight decreases, then the reverse is true. Similarly, with the deployment of flaps and undercarriage, the curve will move up and left, showing that the power required increases, but the performance speeds reduce. Again, the reverse is true when the gear and flaps are retracted. Hopefully from this demonstration, you can see the importance of using a graph for the reference speeds. The principles you have learnt form a large part of the requirements of the ATPL examination, but more importantly, these principles will allow you to make accurate and informed decisions in routine flight management, and especially in emergency situations where your training becomes a vital safety cushion. This completes the lesson on the general performance principles in the cruise.